Shalom, Hello everyone, my name is Hayom. In this series of videos, I'm going to implement transformers from scratch with you. And in this particular video, I'm going to implement self-attention. You can see this in this architecture. This is a architecture of self-attention. Actually, the attention mechanism has been studied for many years, but only in recent years it has been used in deep learning. And transformer is an important model that was proposed in the paper. Attention is all you need. So if you are learning deep learning, you have to know transformer because it has been widely used in CV and NLP. So yeah, in this series of video, I'm going to implement transformer from scratch, so you can know what is happening under the hood. And you can this is architecture of self-attention. At first, we have 4 embeddings. What is embedding? For example, if we have 4 words, and I like reading books, and you convert each word into an embedding. I'm not going to how to convert it. Now we have 4 embedding, each 4, and namely 4 vectors. Each vector represent a word. So just for easily just to easily demonstrate it, I'm going to say the length of vector is 2, and we use 4 matrix to convert the vector A1 into Q1, K1, and V1, and this is just a matrix multiplication. So this query is the key, is the value, and then we for each embedding, it was converted into 3 vectors and QKV, and we use Q and K. You can see the formula here. Now we need to calculate the attention score. This is a formula proposed in attention is all you need. So it's not a difficult formula. You just need to calculate. It's just matrix multiplication, and you use this to I mean, in the paper, the why you have to divide it by this is if you do not divide it this, and if, for example, if the decay is very long and the gradient might be small, it just make if you don't scale it, the result might be 0.99, and the other also amount to 0.001, so it's not balanced. And after you say it's more balanced, it's like 0.8, 0.1, and 0.1, and you use the attention score to you use this score to multiply V, and to get the new V. So yeah, I'm not finished yet. So you can see that the 4 attention scores is 0.2, and the 4 attention score, and you multiply each attention score with V and sum them up. Now we got a new B1. So this B1 fused information from A2, A3, and A4. So I want to demonstrate that the main focus of this video is not the concepts. So the main goal is coding. So I'm going to code self-attention from scratch. If you are not fully understand with theory, you can see other tutorials. Yeah, I'm going to import. We create a class called self-attention, inherited from n.module. init function. We need to send three parameters here, which is the length of A1, the length of K and Q. I want to mention that the length of Q is equal to the length of K, unless you can't do this, right? So and the length of Q it can be a different number. So we need three numbers. Now we are going to implement three matrix, and we just use n dot linear, right? And this is the length of A, and this is the length of K, and I think. And let's see it in the WK, and this is actually is W1. Okay. The input length, the output length, I think QK, yeah. Okay, I think Q. We use this three matrix to convert A into QKV. Okay. Yeah, that's okay. We can, I think, 3 W A to Q A to K A to V. Yes, that's what the three functions does. And we need to now we're going to implement forward function. The only input of the forward function is A, right? It's just here. Yeah, the only thing we send in is here. I know in this I'm sending for A1, A2, A3, A4 simultaneously. This is implemented by matrix. So, but actually A is a stacking of the A1, A2, A3, and A4. This is a parallelization of calculation. query equals self dot. Query key Yes, now we're going to calculate attention scores, right? We are going to just implementing this. We are now going to implement this formula with a few lines of code, and this means matrix multiplication, and you can also use touch dot mat mod, and I'm going to use it. We are going to transpose the last two dimension, and this is scaling. Scale. We already have the self dot scale, so we just need to multiply it with that. And this is here, right? So yeah, I think this part is finished. Now we need to calculate it with v. Also we need to solve max. We need to solve max, right? Because attention is a tensor, so you can use softmax, and you also want to specify -1. This means you calculate. You know the sum of softmax outputs is 1, so it means the last dimension, the sum of last dimension is 1, and yes, x is output. So we have the attention score, and yes, also matrix multiplication value. We already had the value, right? Yeah, I think that's now we are sending the new value x. So we just modifying the values because at first the value only contain the information of the self, and after that the values, each value contains value from other embedding. So it has, it's more global, right? And yeah, that's it's very easy, right? Just a few lines of code and the self-attention. I think it's typo here, right? Yes, attention. I think. Oh, I'm sorry. There. I think it's self dot scale. Right, I'm going to test it. A equals 1, 4, 2. Let me say it. 1 means batch size. Now we have only one batch. So the 4 means we have 4 words, namely 4 embeddings. And 2 means the DA. 2 means DA, right? The length of each embedding. In actual case, it might be much longer, but that doesn't matter, right? And we need to implement a self-attention function. And we need to send 3 parameters here, right? DA equals 2, And actually, you can set whatever value you want to dk and dv. But if you want to iterate with self-attention, for example, you want to use self-attention for many times, you have to make dv equals da. But if you only use it one time, you can set it to 3 or 5 or whatever you want. But if you want to use self-attention many times, you must set dv equals da. So I'm also going to set dv equals 2, right? I'm going to make this can be whatever you want. So I'm going to set it to 3. You can also set it to 5. And yeah, that's a function. That's the function we set, and b equals is the output. Yes, and because this two is the same, you can also use c self tension, right? Because in this function, the input is exactly as same as the output, so you can use this many times. So you can even try it yourself, but I'm not going to use it. And print. Yeah, I think it was finished. So let's run it. It takes several seconds. So this because this I'm sorry, there's something has no attribute dk. I think I missed a right. We can see. Oh yes, I missed it. I think. I'm sorry. Yeah. I also need to. Yes, I think. Oh. Yes, I think it worked. So this is a original embedding. We have 4 embedding. Now, at first, they only represent itself, but after we, for example, we add it. For example, we use 0.1 times the second embedding and add it to the first embedding. Now the first embedding contains the information of the second embedding. So the intuition of transformer and of it's very easy. It's just fusing them together, right? And so now it's the first embedding contains information of these 3 embeddings. So you can see that here the shape is of the input and output exactly the same. So actually you can use self-attention one more time. So the output is also of this shape. Yeah, so I think that's about this video. In this video, I'm talk about the theory shortly. Actually you can I have to say it again that the main focus of this series of video is code implementation. So if you are not familiar with the theory, you can see other tutorials, and yes, and this is a whole architecture, and this the code, the implementation of self-attention. After in the next video, I'm going to implement multi-hand self-attention using it as a basic building block. So if you want to implement transformer with me, you can subscribe my channel and thank you for watching. Thank you. Yes, thank you.